Okay, this is the last topic in chapter 6, and it's about electric motors. And we're going to study DC motors. In particular, we'll be studying armature controlled DC motors. A DC motor consists of rotor and a stator, and rotor is a part that can spin, and stator, for the case of armature controlled motor, is a permanent magnet. Okay? And the armature control is the most common. It's the most common technique to control a DC motor. So stator has a permanent magnet just so that we can provide a constant magnetic flux. Okay? If you remember from physics 2, the torque is proportional to the current in the magnetic flux. And by keeping the magnetic flux constant, now torque can be completely controlled by the current amount of current that goes through. And the back EMF is proportional to the motor speed and the magnetic flux. And again, it's now it's determined by the motor speed. Let's look at the schematic picture. This is from the textbook. So this is the armature circuit. This is input voltage that you supply, and this is the resistance and the inductance of the armature circuit. And then here, right here, VB stands for the voltage drop. It's the back EMF due to the rotor, and this back EMF is proportional to the speed of the motor. Okay, the flux is incorporated into the KB. The torque that's applied to the motor. Okay, now this is the direction of the spin. Okay, and then torque is in the same direction, is proportional to the current. The current in the armature circuit. So the system model looks like this. When you look at the circuit alone, you have the supply voltage, VA. Okay, here we go, VA. Minus the voltage across the resistor. And then you have the voltage across the inductor. And this is the back EMF due to the rotor. Okay? And if you look at the rotor model of the mechanical side, okay, I'm going to change the variable. Okay, we've been using J in the textbook, but I'm going to change to J. We've been using I for the mass moment of inertia. I'm going to change that to J so that I can distinguish between small I, the current I, and the mass moment J. Okay? And it says sum of the torque. The sum of the torque, which is on the right hand side, equals to J times the angular acceleration alpha. Another name for the angular acceleration is the omega dot, or the d omega over dt. Okay? On the right hand side, the sum of the torque consists of the supply torque from the armature circuit, that's this T, which is also proportional to the current, and minus some kind of a damping. The next one is some kind of damping term. So this is some kind of damping term, C. And then this is the load torque, TL. Okay, L stands for the load. Okay. So there are two inputs in the system: the supply, the armature voltage V that you supply, and the load that the motor needs to carry. So we have these two system models. So let me see. So we have two equations and two unknowns. What are the unknowns? The unknowns of this equation, these two equations, it's a set of equations, is the current IA in the armature circuit, and then you don't know what the speed of the motor is. Okay, these two are your unknowns, and you have two equations. So it's only natural to ask for what's the system model. Okay, find the system model. So I have two outputs. That the current, now it's in the S domain, and the speed, motor speed, were the inputs of the supply voltage and the load torque. Okay, so you can have combination of four transfer functions. Four transfer functions are possible from the set of two outputs and two inputs. So the reason why you're looking for the transfer function is because it's actually certainly much easier than finding the differential equation Okay, stay in the time domain and find the differential equation in terms of I only. So if I ask you to write this as a one equation, okay, write this as a one equation in terms of I, okay, I only, it'll be pretty difficult to do. Why? Because you have an omega that you have to get rid of, that appears twice in the next equation. Let me think. It might not be as bad actually. I will just solve for the omega from the equation 1, the first equation, and I plug it into here and plug into here. Okay, and then I'll have an equation in terms of I. But anyway, from the previous chapters, previous sections, you know that it's very difficult to say in the time domain. It's actually easier to just move over to transform, take the Laplace transform and work in the S domain. So in S domain, those two equations will look like this. Let me see if I can remember this. You have a supply voltage VA equals, in the S domain, equals, you have V is equal to IR, you have the current times R plus L S times IA S. Okay, what else did it have? And you had the back EMF, which was proportional to K times omega S. Okay, so this is equation 1 in the Laplace domain. Let me see if I got this one right. Here we go. Okay, so that was KB. Okay, KB, which is same as KT. Oh, by the way, these are called this is called the motor constant, or the torque constant. Okay, they are the same numbers actually for motor. Okay, so the KB or the KT, they're the same numbers. So from now on, I can actually write just a K. Yeah, I can just write K. So let's see the second equation. If I take a Laplace transform of the second equation, sum of the moment, which was equal to, okay, I'm gonna put the sum of the moment on the right hand side, which is equal to J times S times omega S. Okay, sum of the moment is equal to I alpha, and the sum of the moment, what was it? Equals, here it is, I'm trying to write this one, C omega plus C omega plus C times omega, and the torque that's applied by the armature current, which is equal to K times I A S. Okay, and I believe that's equal to minus the load torque. Okay, so this is the second equation. Let me check one more time whether I got this right. I moved C omega to the left hand side, T to the left hand side, so it's positive, positive, negative, and then the right hand side you only have a negative TL left. Let's see. Okay, plus minus, perfect. Okay, perfect. So now I'm just not gonna mess around with the substitution. I'm just gonna solve for, what's my goal? I'm gonna solve for the IA sub S. Solve for the IA and separately, okay, omega sub S. Okay? So we have two equations and two unknowns. I want to solve for each unknown. So the best thing for me to do is, I just love Cramer's rule. Okay, I just cannot help myself. I don't like to do any substitution. So if you wanted to do substitution, I will solve for omega from here, from the first equation, and I'll substitute it into the second equation. So that way I can get rid of omega. Or, like I said, I just like Cramer's rule, because that's the only way I can solve simultaneous equations accurately, unfortunately. So let's say the first equation is LS plus R times current plus K times omega, and the second equation, coefficient of I is negative K, and the coefficient of omega is JS plus C, some damping constant. Okay, equals your V supply voltage, or the armature voltage, minus, and you have a load torque. Okay, so once I put it in the matrix form, my current is Okay, it's a big fraction. In the denominator will be the determinant of the matrix LS plus R, the coefficient matrix. And on the numerator will be the coefficient of I, which is the first column, will be taken out and replaced with the VA and TL. So now it becomes LS plus R, JS plus C. Okay, that's how you can find the determinant of the 2 by 2 matrix, AD minus BC. Then you have a double negative, so you have plus K square in the denominator. And then you'll have, now multiply these two together, so you have a JS plus C times VA sub S. Now multiply these two together and subtract from the first. You have plus K times TL sub S. So now I found actually two transfer functions. So if you wanted to find the IA divided by VA, what you do is you look at the coefficient of VA. Okay, when you solve for the IA. So should I rewrite it? I'm just gonna write down the answer. VA sub S equals JS plus C divided by the denominator. At this point, sure, I'm just gonna multiply them out. L times J S squared plus, look at that, LC plus RJ S plus RC plus K square. Okay, that's going to be, this is the transfer function of the I divided by VA. And then if you want the second transfer function, IA sub S divided by the load torque equals K divided by the same denominator. Okay, and then this was pointed out to you a long time ago, that the transfer function of a same system, of one system, you may have many different transfer functions, but they all have the same denominator. They all share the same characteristic equation. Okay, so I'm just going to highlight that one. Okay, here we go. Okay, so this is important. That's why I highlighted with the bright yellow. So this is called the characteristic equation. And then they're all the same. They're the same in every single transfer function, as long as you're talking about the same system. That means they share the exact same characteristic root. Their homogeneous solutions will look the same, with the exception of having different constant of integration. So let's see. So if you want to continue, okay, So right now I found transfer function I divided by V, and I found another transfer function I divided by TL, the torque. If you want to find the transfer function omega, I meant to write omega sub S divided by VA sub S, and then omega divided by the load torque, you'll have to repeat the process. Okay, you have to repeat the process starting from right here. Okay, starting from right here. Now I can no longer see what I wrote. Oh, here it is. Okay, and solve for the omega. Okay, omega sub S, you'll have the same identical, okay, same denominator, and on the top, what you do is you take out the second column, which is the coefficient matrix of the of the omega, yeah, and then replace it with the inputs VA and minus TL sub S. Okay, so this will have the exact same denominator, and then for the, let me see, if you multiply this one first, you have a minus LS plus R times T load minus, and then there's a double negative, so plus K times VA sub S. So let's see if we can pick out the transfer function. This will be the transfer function omega divided by VA. The other one. Okay, this is a transfer function right here. This is a transfer function omega divided by the load torque. Let me pick a different color. Let me see. How about purple? Okay, purple. And this term right here. Okay, k divided by the same denominator. That's a transfer function, omega divided by VA. Okay. So what's the benefit of having a transfer function? So let me see if I have any more space. Okay, I think I can make a little more space. Okay. So let's take one transfer function. So let's take, sure, why not? This looks good. IA sub s divided by TL sub s. Okay, that's k divided by all the same denominator. Okay, and when you cross multiply, you have LJ s squared plus LC plus RJ s plus RC plus k squared. The current equals k times TL sub s. Okay, so now we have a differential equation. Okay, and then this differential equation will give you the whose solution will give you the response, the current response due to the load torque. Okay, it's not the total response. So in time domain, you have LJ, second derivative of I, with respect to t squared plus LC plus RJ, the first derivative, plus RC plus k squared, current equals k times the torque in time domain. Okay, so here I like to stress this I right here. Okay, is the current due to the load torque only. Okay, and if you remember, because all the initial conditions are set, solution to this differential equation will only be the forced response. Okay, so now let's see. Oh, let's skip that one. Let me see. I think this is the end. Actually, this is the end of the electric motors. Oh, actually, it was split into two sections. So now let's talk about the motor performance. Okay, so what's not said here is it's a steady state. Okay, it's a steady state motor response. Okay, when they talk about the performance, they don't talk about the transient response. They talk about the steady state response. Now, and then you have to be familiar with these terms: no load speed, no load current. What do they mean? Stall torque, stall current. What do they mean? Well, you need to learn these terms. Why? Because when you're shopping for DC motors next year for controls lab, you'll be asking these questions. Oh, how do I choose motors? Well, you'll be given these numbers and what do they mean? Okay. So let's start with the system model for the DC motor. So this one, let's see, I changed the notation. I changed the VA into V input, okay, with the current, armature current. I was tired of writing A, so I just changed just the current I. Let me see. And of course the moment of inertia, I changed to J, okay. So somehow, like, these equations look better to me. So now this is about the steady state response. So what you do is you set, okay, it's a steady equation. So what you do is you set any derivative with respect to time to be 0. Why? Because you're looking for the response. I sub t, you replace, okay, you replace anything that's a function of time with a steady state value. Okay, so this will just drop out. This will drop out. You're only left with these terms, okay, and which is written down here. So V in is the nominal voltage. When you buy a DC motor, it will tell you it's supposed to run at 12 volt motor, 12 volt or 6 volt, 7 volt. It will tell you what's the optimal voltage it's supposed to apply, but it does not mean that you cannot supply different values. So even if you buy a 12 volt motor, you could certainly supply, let's say 10 volt, okay, 10 volt, and it will still run, okay, although it will be at a slower speed. So we have our basic static equations. So when somebody says, okay, no load speed, and find, no load speed and a no load current, what that means is that this is the value of the speed, omega, and the current when what? The load torque is equal to zero. Okay, this term will disappear. So what are we doing? We're trying to solve for what are the unknowns? What's the voltage? This will be given. This will be just given. It will just tell you from the beginning. It will tell you, oh, this is a 12-volt motor. So you're supposed to supply 12 volt. So this will be given. Now, this will be probably the very name of the motor. So now you could solve for it. Oof, do I need to solve for this? Okay, what do you think the steady state current is? What do you think the no load current? So this one, if I were to change my notation again, will be I no load, okay, equals, do I dare use the Kramer's rule one more time, or do I want to do substitution? Whichever, okay, whichever. So I happen to love Kramer's rule. Okay, equals 0. So I replace this equation with the second one. I'm gonna use the Kramer's rule. Why not? So I have a denominator is the determinant of R, K minus C. In the numerator is, what do? I take out the first column, right? R and K, and then replace with the V in and 0 and K and negative C. So that's equal to negative RC minus K squared in the denominator, and then you'll have negative C times V in. Yeah. So when they tell you the no load current is 20 milliamps, that's what this is. So you can actually reverse engineer, and then figure out what these values might be. Yeah. So you can do the you can use a similar method to find the no load speed, omega no load. So this is part of your quiz, I believe. So denominator the same, minus RC minus K squared. In the numerator, you take out the second column, which is K and negative C, and replace with the right hand side. Okay, here we go. This is a 0, and the other diagonal is negative K. So it'll be K divided by RC plus K squared V in. Here it is. Okay, so that's the other expressions for the no load speed and the no load current. How about the stall torque and the stall current? Same thing. Okay, so in that case, you're looking for the load torque. Okay, this is your negative stall torque. I don't think I need to write down torque. This is your stall torque, and the stall current is that one. So this is your I, the stall current. Okay, and then again, what is the V in? Well, whatever they tell you. Yeah. So a lot of times in the data sheet, like depends on how much you pay for the motor. If you pay $500 for it, they'll tell you what is R, what is K, what is C, everything. Okay, let's say you pick up a motor from somewhere. Okay, didn't come with a data sheet. Well, you don't know. Okay, maybe you can find something somewhere on the internet, and then say, oh, you might be able to find these values: stall torque, stall current, or the no load speed and the no load current. And then sometimes you might have to just reverse engineer and find out, oh, what is the resistance, what is the K, what is C. You can reverse, you can just go back. You can, given those values, given those currents and the speed and the stall torque, you can find those values. So let's see. So here, this is actually easier than I thought. I'm trying to look for the stall current. So from looking at this, your stall current, the first equation gives you stall current is V in divided by R. Okay, and then the load torque. Stall torque is equal to K times I of the stall, which is K times V in divided by R. Okay, here it is. Okay. So I don't want you to be, when you're shopping for a motor, I don't want you to be afraid. And then these are the values. This is how you find those values given the motor properties. Another thing to note, the thing about the stall torque and the stall current, okay, you absolutely do not have that, right? If the motor wants to run, and if you prevent it from running by applying the stall torque, I think your motor might burn out. Okay? So I think this is the end of chapter 6. Let me see. There's no more. Okay, there's no more. And then there might be a couple of homework problems. And so now I'll see you back for chapter not 7, 8. Okay. Our next lecture is going to be about chapter 8. Okay. I'll see you then. Okay, bye. Ooh, how do I delete